Hi, this is Jonathan Gardner. We're doing Introduction to Calculus-Based Physics. And this section is an introductory section where we're going to cover some of the basics of algebra that you should have already learned. Maybe some of these things are new. At least I'm going to present them in kind of a high level. If there's details that you're not familiar with or you've forgotten, then you know what to review now. There we go. All right, so the topics we're going to cover are numbers, arithmetic, which is what you can do with those numbers, and then we're going to talk about expressions and equations, which is the meat and bones of algebra. And finally, I'm going to cover some of the intuition that you need to get from algebra. So first, numbers. So originally, numbers were an adjective that you would apply to a noun, describing how many of those noun things that you had. And so numbers were tied to something concrete, so like 2 gallons, 2 ducks, or 2 meters. And even today, in many languages, numbers are still adjectives. And so they're not something that you think of as something that can exist independent of the thing that it's counting. But in math, we do that abstract thinking. We do treat numbers as if they're something else entirely. So we can say 2 plus 2 equals 4 without knowing whether it's 4 gallons or 4 ducks or whatever. And then we can use that to work backwards and say then that means that 2 gallons plus 2 gallons makes 4 gallons. And it's important to realize that in math we're dealing with abstract numbers that exist along with the perfect circles and perfect triangles, not in this universe, but somewhere in this Platonic reality. In physics, we deal with concrete numbers. So every number has a unit associated with it, even if it's just counting things. So in physics, you're going to be asking, like, what units are we dealing with? Are we dealing with kilograms or meters or whatever it is? So, but in math, we just worry about the abstract numbers. Thankfully, when we do physics, it looks like math. And so math happens to work for reality, which is great. The types of numbers you encounter when you were first a child, you learned how to count 1, 2, 3, 4, I'm sure. And then somebody told you about 0. So how many cats do I have? I have 0 cats, which is, for a little kid, is just an amazing concept. And then somewhere along the line, somebody told you about negative numbers, which are like the opposite of the counting numbers. One way to think of negative numbers is it's how much money you have if you borrow money from your friend. Then combine those all together, you get the integers. And we deal a lot with integers in math. They go from negative infinity all the way. Well, infinity is not part of the integers, but they go from arbitrarily large negative numbers to arbitrarily large positive numbers. Then with the integers, you can build a set of rational numbers. Rational comes from the word ratio, where you have something divided by something, a over b, where a and b are both integers. And this, of course, includes all integers because 3 is the same as 3 over 1. And if you're going to do geometry in Cartesian coordinates, stuff like that, you're going to discover quickly that the rational numbers are not enough to describe all the quantities you're going to find. That you need additional numbers called irrational numbers, ones that cannot be expressed as ratios of 2 integers. These are numbers like pi and Euler's constant e and the square root of 2. And so with the irrational and irrational numbers combined, you get a set of numbers called the real numbers. In physics, we deal a lot with real numbers. But those are not the only numbers out there. There's imaginary numbers like I being the number that if you multiply it by itself, you get -1. And then the complex numbers, which include real plus imaginary numbers combined together. And then, of course, we have vectors and tensors and matrices and all these other things that exist in math that physicists use all the time, especially the vectors. And later on, I don't know if we'll cover it in this introductory course, but there's this concept of tensors as well. But we deal mostly with real numbers in physics, although you will see a use for the imaginary numbers, and we will do a lot with vectors when we get to 3 dimensions and things like that. So that's pretty much all that how we have to say on numbers. Let's talk about what we can do with these numbers. So of course we can add and subtract. Adding means you're taking things that are similar and grouping them together. So you have 2 ducks over here and 3 ducks over there, so that means you have 5 ducks altogether. And subtraction is basically the opposite. You're taking away. So if you start with 5 ducks and you take away 3 ducks, we say 5 ducks minus 3 ducks makes 2 ducks. And subtraction is really adding a negative. So if you think of it as you start with 5 ducks and you add -3 ducks, so basically you add a loan that you owe 3 ducks for, then you really only have 2 ducks. And if you get confused on whether you should add or subtract when you're combining different signs, the rule is really simple. If the signs are the same, you keep the signs and add it. So -5 plus -3 is -8. You keep the sign, you just add those numbers. If the signs are different, then you keep the sign of the bigger one and you subtract. So 5 plus -3. You keep the positive sign because 5 is bigger than 3. And so it's +2 because that's the difference between 5 and 3. That's the simple rule. And we describe in physics, we often talk about the parts of addition. So we take terms, you add them to other terms, and you get a sum. So we'll often hear the words term and sum used, meaning this. One thing to understand about addition is that if you add the same number or similar size numbers again and again, you get something called linear growth. So this is like a series 2, 4, 6, 8, 10, 12, 14, 16, 18. It's going to take a long time to get to a very large number, but you can get there eventually. It's like walking down the street or driving down the freeway or time passing. Another thing to note is that when you add reals, and this doesn't apply to all numbers, but when you add reals, it's commutative, meaning that it doesn't matter what order you add it in. A plus B is the same as B plus A. And this isn't true for all numbers. So just note that it's true for reals, which is pretty much all we're going to deal with in this introduction to physics. It's also associative. When you're adding 3 terms together, you can add the first 2 terms or the second 2 terms and then add the remaining term. It doesn't matter. Then there's this concept of identity. The identity in addition is 0. When you add 0, nothing happens. So A plus 0, it doesn't matter what A is always A. It doesn't change anything. And that 0 can appear in a number of different forms. When we do a process called completing the square, for instance, we're going to add 0 by adding plus of a quantity plus its negative, so that we get those two will cancel itself out and add to 0 together. So that's the inverse operation. Is if you have something you want to get rid of it, you just add its negative. So -5 plus 5 would give you 0. Next, you get the concept of multiplying. Multiplying means groups of. So 3 groups of 5 ducks makes 15 ducks altogether. And really what it means is you take, when you have A times B, you're just taking A and adding itself to its. You're adding itself B times, basically. When you multiply by a negative, it switches the sign. Hopefully 5 times -3 is -15, doesn't surprise you. -5 times -3 would be +15. And dividing is kind of the inverse operation of multiplying. It means to find the number of groups or find the number in each group. So 15 ducks divided by 3 makes 5 ducks. So that says that there's 5 ducks in 3 groups when you have 15 ducks altogether. Or 15 ducks divided by 5 ducks makes 3. So that's what dividing means. And just like subtraction is adding the inverse, dividing is multiplying by the inverse, but not the additive inverse, the multiplication inverse. And the inverse is just the number flipped upside down. So A divided by B is the same as A times 1 over B, or we just write it A over B. That's why you don't see the division sign with the 2 dots in algebra text. You always see it as a fraction. The names, it's a factor times a factor is product. You're going to hear product, you're going to hear factor all the time, so get used to those terms. And the notation. So if we just write AB, that means we're multiplying A times B, and we just use a dot or an X, usually the dot. Usually we just leave it out altogether. So for dividing, we have the dividend, that's the thing you're dividing up. The divisor, that's how you're dividing it. And the quotient is the result. So, and in fractions, we have a numerator, we have a denominator. So you're going to hear that a lot. And just a note, multiplying fractions is ridiculously easy. You just multiply the tops and you multiply the bottoms to get the result. So, multiplication. When you multiply the same or similar number over and over again, you get an exponential growth. 2, 4, 8, 16, 32, 64, 128, 256, 512. It just grows ridiculously fast. Multiplication of reals is commutative, just like it is for addition. So AB is the same as BA. So 5 times 3 is the same as 3 times 5. Multiplication of reals is associative. So we have A times B times C. You can multiply A times B first or B times C first. Doesn't matter. The identity is 1. So 1 times A is always equal to A. You always multiply by 1. It doesn't change anything. And the inverse is the number flipped over as a fraction. So when you multiply A times 1 over A, you always get 1. Unless A is 0, of course, because you can't, when you multiply anything by 0, you get 0, and you cannot divide by 0. It just makes no sense. A good way to think about this division by 0 thing is like that statement. This statement is false. That's what it means to divide by 0. So it has absolutely no meaning at all. It doesn't make any sense at all. This is something we do literally all the time. And when I started physics in college, I completed calculus in high school and things like that. It just struck me how often we were doing this, finding common factors. And the middle step is often skipped, okay? Because immediately when you see 15/9, you should immediately say, oh, that's 5 times 3 over 3 times 3. Get rid of the 3's, it's 5/3, okay? If you're not able to do that, then you're going to have a hard time in algebra. So you need to know what the factors are of these different numbers. But also, if it's like 5a divided by 9a, you divide the a's, and you have 5/9, right? Okay, adding fractions. For some reason, this is the singular most confusing thing in all of arithmetic. It's the one thing that keeps people basically out of high school and on to college. The reason why is it's difficult. It requires like 3 or 4 steps to do it right. It requires finding factors, actually finding multiples. And if you're not good at your multiplication table, you're going to have a hard time doing this. Okay. The first thing to realize is that when you're adding a over b plus c over d, you cannot add those initially because the denominators must be the same to add. What you're seeing is you're basically seeing like we have a cats and c dogs. How many elephants do we have? It doesn't make any sense, right? So you need to find a common denominator. So, and if you can't find a common denominator, then just multiply the bottoms by each other for a common denominator. Next, you multiply each term by 1, but you rewrite that 1 as something over something. So you take, like for instance, we take a over b times d over d, and c over d times b over b, and now we have ad over bd, and we have cb over db. And you just add the numerators. That's all it is. And so the end result of this process, no matter what the factors are, is AD plus CB over BD. Now, if you were able to find factors, you can short circuit some of the simplification that you'll have to do later. So you're going to save yourself some time. But really, if you don't know the factors, you can just go ahead and multiply like this and you'll get the answer. So if you're not good at adding fractions, you need to get good at it. Distribution. Okay. This is one of the first things they teach in algebra. And it's the one thing I found that basically you have to do it all the time. Okay. When you have something times a sum, then that something gets multiplied by each term. So a times b plus c is the same as ab plus ac, and it works in reverse. If you see that you have multiple terms with the same factors, you can factor out that factor. So ab plus ac is a times b plus c. And when you have something plus something times something plus something, you have to do the cross terms. This is the FOIL method that you might have heard about. First, outer, inner, last. So first we have AC, then we have AD, the outer terms, and then the inner terms BC, and then the last terms BD. So that makes 4 terms. Okay. If you can recognize this pattern in algebra, you're going to be way ahead of everybody else. So just study this pattern. Finally, I want to point out that if you have not memorized your addition and multiplication tables, and multiplication probably up to 12 or 13 at least, you're going to have a hard time. So just memorize the multiplication tables, memorize the addition tables. The bigger factors, you're going to get used to seeing them again and again. So, but if you don't know what 8 times 7 is off the top of your head, you're going to have a hard time. So just take the time and memorize it. It's not that hard. There's really not that many of them. Okay. Let's keep going on arithmetic. This is something that they don't teach in grade school, typically. But just like multiplication is adding a bunch of times, we have this thing called exponents, or indices is what I think they call them in the English system, the Great Britain, whatever. So we write it a with a superscript n, and that means you're basically multiplying a by itself n times. And if it's negative, then you're really dividing by that n times. So, and that makes sense because if you think about it, if you take a to the negative n and you multiply by a, you're just getting rid of one of those negative n's and you're increasing it. That's the rule down below. When you're multiplying things with a common base, you're adding the exponents. And finally, the other rule is a to a fraction, where the denominator is in, is just the nth root of a. Okay, so that's the number that multiplied by itself would give you a if you multiplied n times. And 2 little notes that if you're multiplying the common base, you add the exponents. If you're taking the exponent of an exponent, you just multiply the exponents. So pretty common. You see these a lot. Logarithms. When I was taught algebra and trigonometry in the school system as I went through the 90s. This was like one of the last things we learned in trigonometry, and honestly, I wish it was one of the first things that was introduced. So if you want to go reverse, you can take logarithms. Logarithm is kind of like the division compared to multiplication. So logarithms are to exponents as division is to multiplication, as subtraction is to addition. So log base a of a to the n is n. That's the basic rule right there. That's the pattern. Okay. And we have two common bases that we see. One is a natural base and the exponent. Natural base is called ln. It's just log base e being Euler's constant. And this e quantity arises a lot in calculus. It arises in physics as well. The common base is 10. If you see log by itself, we generally mean log base 10. If you're in computer science, they mean log base 2, but we're not doing computer science, we're doing physics. So log base 10. Couple interesting notes is if you have the log of a product, that's the same as the log of the sums. Okay, so log of AB is the same as log A plus log B, and this is how slide rules work. And if you don't understand why this works with slide rules, I implore you to go look at a slide rule and think about this until you can figure it out. Once you understand it, you're going to understand a ton about logarithms. The second thing is that if log of anything to B is just B log A. So, and something you do commonly is you change base. So if you're in base A and you want to go to base B, log base A of x is the same as log base B of x divided by log base B of A. Okay. And exponential growth gave us like 2, 4, 8, 16, 32, that kind of thing. Logarithmic growth gives us numbers that increasingly that start off going faster, that seem to be going fast, but then they rapidly approach kind of a plateau. So as you can see, this series here, I forget where I got this from, but it was I think it was log base 2 of numbers that were increasing. But anyway, as you can see, it's like approaching like 60 or 65 or something like that. It starts off increasing by tens, then it's increasing by fives, and then twos, and then finally it's just increasing by ones. Logarithmic growth turns exponential growth into linear growth. And so if you want to analyze an exponential series, you often take the logarithm of that so you can see the line. So, okay, order of operations. So when you're doing your arithmetic, you have to think about what do you do first. Basically, it's just parentheses, exponents, multiplication, addition, or PEMDAS, parentheses, exponents, multiplication, division, and addition and subtraction. Do those in that order, you'll be fine. That's not hard. If you're confused about what to do first, if you're one of those guys that got taken in by that stupid Facebook meme where it's like 1 plus 1 plus 1 times 0 equals what? Yeah, you need to review your order of operations. Okay, now we're on to expressions and equations. This is what people tend to think of as algebra, but honestly, the algebra has already been done. We've already talked about arithmetic and numbers. Now we're just basically writing it down when we don't know the numbers. So the first rule of algebra is you need to get away from the mindset that the numbers on the paper are fixed and you can't do anything to them. You know the rules of what you can do to numbers, what you can't do to numbers. Go ahead and do it. Just try things out, you know. And there's usually more than one way to solve problems. And a good experiment, a good fun thing to do in algebra is to find more than one way to do it, or find them all. See if you can find all the way to do it. Another thing to remind yourself is that this is seriously fun stuff. It is algebra, you know, having done calculus and geometry and all this advanced mathematics. Algebra is where the puzzles are at. It's, you know, it's amazing to see professors just one little trick in algebra to solve the formula they're working on, and they're just like, yeah, they just get seriously excited about it. So this is some fun stuff. First thing is variables. So we've been using A, B, C's, and those are just variables. Variables are basically hold-ins for any number. Okay. Oftentimes we want to find out which number or numbers work. So variables are like placeholders, like the answer goes here. So you can use any letter of any alphabet, but we tend to stick to Latin and Greek. So you might want to learn your Greek letters: alpha, beta, gamma, delta, uppercase and lowercase. I think throughout the introduction series, we're going to cover pretty much most of them. There's only a couple we don't cover. Note that we can only use one letter. So if you see CAT, it's not cat, it's C times A times T. And if you want to be more descriptive with your variable names, or if you have a conflict where you want to use the same variable name twice, you can use subscripts to distinguish them. So like if I want to use A for elephants and A for cats, then I can keep them separate by using a subscript. And numeric subscripts generally indicate an element of a series, so A1, A2, A3. So if you see numbers at the bottom, it generally means that it's part of a series, although not necessarily so. Okay, so expressions. expressions are what you do when you don't have an equal sign. So an expression might be x squared plus 2x plus 6. And this is just something. It's just an expression. And what do you do with expressions? Well, you can modify them. You can modify them by adding 0 or by multiplying by 1. And when I say adding 0, I mean like adding by something and then subtracting, adding by something and adding its inverse so that you get 0 in the end. And when you multiply by 1, you're really multiplying by something over something, which is equal to 1. Okay. And when you do this, you're not changing the expression. Just make sure you're modifying the entire expression. You're not changing the value of it. Of course, we could change the value if we really wanted to, but it won't be the same. And we're going to be changing the values of expressions when we manipulate equations. But we need to keep in mind that the expressions have changed their values, right? They're not the same. They've been modified. So usually, when we look at an expression, we want to simplify it into its simplest form. And I put this in quotes because what is the simplest form can be a matter of debate. Okay. There's generally 2 or 3 ways you could write an expression in a simple form. One way showing all the factors, another way showing all the terms. But generally, what we mean by simplest form is just combine like terms. So if you 3a plus 4a, you just write down 7a. You just combine the like terms, you move them around. And as I mentioned, we sometimes want to modify these so we can factor out things. So an equation arises when you have an equal sign or a comparative like greater than or less than or something like that. And equations are really where all the magic happens. With an equation, we can see how the variables inside those equations relate to each other. And we can manipulate these equations by applying some operation to both sides. As long as you're doing it to both sides equally, the equation will remain balanced. And this is the important thing. You can add, you can subtract, you can multiply, you can divide, you can take the exponents or the log. You can do any number of things as long as it applies equally to both sides. And usually what we're trying to do when we take an equation and manipulate it is we're trying to get it to tell us the answer. So when there's a complicated equation, we just want to simplify it and manipulate it until we can say, oh, x is this. Okay. Here's an example of what I mean by manipulating equations. So we start off with an equation 4x squared minus 9 equals 0. Okay. In that statement alone, 4x squared minus 9 equals 0, is the information that x can only be one of 2 values. However, to me, I can't see it right away. So what I do is I start manipulating. First, I add 9 to both sides. I get 4x squared equals 9. Then I divide both sides by 4, so I get x squared equals 9 fourths. Then I take the square root of both sides. X equals plus or minus square root of 9 fourths. It's plus or minus because x could be positive or negative. If it's positive or negative, you square it, you're going to get the same answer. Right? It's going to both be positive. And then so the square root of 9 fourths is 3 halves. And so x could be positive, negative 3 halves. And indeed, if I put those values into the original equation, I will see that it balances. So all I did was apply simple operations, just adding, dividing, square roots. And the answer literally fell out. So I didn't have to think very hard to get the answer. All I was trying to do was basically simplify. I looked at 4x squared minus 9. And I said, gee, wouldn't it be nice if I had the 4x squared all by itself? And when I had 4x squared by itself, I said, gee, wouldn't it be nice if I just had x squared by itself? And then when I had x squared, I said, gee, wouldn't it be nice if it was just x? You see, and I just applied the operations. I didn't have to think very hard. The answer just fell out. And this is often what happens. Once you get an equation, you should be able to manipulate it into any number of forms. Okay, proportional and inverse proportional. You'll often hear physicists talk about something is proportional to something or something is inversely proportional to something. All they really mean is that there is an equation where it says A, if A is proportional to B, then that means A equals something times B. Okay, and if A is inversely proportional to B, then you say A is equal to something divided by B. And you might hear like A is proportional to B squared or something like that. It just means A is like something times B squared. I use 7 just as a placeholder. It could be any number. And what's important to think about is when you see something like AB equals 7, how do A and B relate? Well, in order to see that, you basically want to solve for A by dividing both sides by B. And you see that A equals 7 over B. So A is inversely proportional to B. Likewise, if you divided by A instead of B, you see that B equals 7 over A. So B is inversely proportional to A. So this is it's a mutually respective association there. If something is proportional to something, then that is proportional to it. Okay. And just with these terms alone, we can determine a lot about how variables behave in equations without actually getting into the math. Okay, so we've learned what the equations and expressions do. Now let's actually try to use it to solve problems. So the way you do this is you first come up with the variables and label them so you don't forget what they mean. And once you have that, then you start taking the problem and rewriting it from English into math form. And this is by far the most hardest step, the most difficult step. Once we have equations, we can manipulate the equations, which is extremely easy to do once you know all the tricks. And then finally, you just read the answer. That's how you solve problems with algebra. It really doesn't, the hardest part is writing down the equations. That's the skill you should be focusing on in algebra. If once you're able to manipulate the equations, then that's the hard part. In physics, we deal with reality. Reality speaks, we think of reality in terms of like whatever language we're thinking in, which is, English in my case. So I have to be able to translate the English into math if I want to use math to solve physics problems. That's an important skill that often gets overlooked when people study algebra. A common type of equation that arises quite frequently is the quadratic equations, which look like x squared plus bx plus c equals 0. Okay, and this can appear in a variety of forms, but you should be able to manipulate it down to this form. Okay, so basically, whenever you see an equation where you only have constant terms, linear terms, and square terms, you can rewrite it into the form above. Okay, if there's a coefficient to the x squared term, for instance, if there's a factor there, then you just divide by that across the board to get 1. And the way we solve this is we first factor the left-hand side into something x plus something equals 0. Okay, and then we say, well, logically, if it's equal to 0, then either x plus c or x plus d must be 0. So x is minus c or x is minus d. That's how you solve quadratic equations. There's really no other way to do it. So the question becomes, well, how do you factor those quadratic, expressions? Well, if you see something that's x squared minus some constant squared, that's x plus ax minus a. Just write that down. If you see something and you recognize the inner term, the linear term is a sum, and the constant term is the product, then you just know what it is. You just write it down, right? But if you're not really sure, or if you're stuck, if you want to make sure, you can use this formula. This formula comes from completing the square, which is a technique that if you get to the point where you want to use that to solve the problem, just use the formula. So, graphs. I was going to show you a bunch of graphs, but I really don't have much time for this video. I'm already at like the 30-minute mark almost. Graphs are curves on an xy plane. They come from equations that relate x and y. Once you learn how to recognize a curve and you learn what equation that relates to, and it really isn't hard. You just have to build up your. It's like going to the zoo. There's like a zoo of graphs out there, and you start to learn that some graphs look like each other, some graphs don't. One draws lines, one draws parabolas. There's cubic curves, there's ellipses, and you start to learn the formulas that give you that graph. And it's just a matter of recognizing and drawing. And unfortunately, this is a skill that I really can't do much justice here. I really have to defer this to the mathematicians that'll tell you what the different graphs can give you. But keep in mind that in physics, oftentimes we do something and we say, oh, that looks like math. And the reason why we recognize it as math is because we've drawn out a graph. And we can look at the graph and say, oh, that almost looks like a line, or that looks like a parabola. And then we know what formula to write down, because we recognize from the graph what equation gives you that graph. Functions. Functions are really, you deal with them in algebra, but really it's more of something that you think about in calculus. Functions are kind of the quantity that you deal with in calculus, whereas in algebra you're dealing more with constants. So functions are named like variables. They use the same naming scheme. Functions can take one or more parameters, and we just write that with parentheses afterwards. This doesn't mean f times the quantity x. It means f takes a parameter. It's confusing, but you'll get used to it. And you just need to think of functions as they're just expressions, and they need something to be substituted in order for it to determine what the result is. And oftentimes, we don't know what the function is, just like we don't know what a variable is in the equations. And we can actually solve for functions. We can actually rewrite an equation that has a function in it where we can get the function all by itself on one side and find out what that function actually is. Mathematicians like to talk about domain and range, but who cares? I actually don't think of things that way. You won't either. Mathematicians are actually thinking about something completely different than physicists are thinking about. So I just kind of the domain and range is interesting for your particular theories about whatever, but we're not going to. Anyway, sometimes we don't write the parameters when we're talk about functions. We just, early on we said f takes x, and we just use f over and over again. Physicists have a nasty habit of having multiple functions that take different parameters, all with the same name. So we might have a function that takes mass or a function that takes length, and we use the same f or same letter. It's just a nasty habit. We shouldn't do it, but we do. You need to know how the variables depend on each other to find the functions. And that's really, after a while with functions, you start to think of them as variables because they're really not that different. And you start thinking about how those variables depend on the other variables based on the equations that exist. So anyway, but it's kind of a premature concept. If you don't know calculus, you don't really understand why it's important to think of functions as something different. But we'll cover that in calculus. Finally, the intuition section. If you want to get an intuitive sense of how algebra works, you need to know how numbers relate to each other. You need to know which numbers are factors of which numbers and things like that. You need to know how to do these operations, these arithmetic operations, the multiplication, division, exponents, and logs, and things like that. You need to know how to manipulate expressions, how to simplify expressions, what you could do to an expression, keep its value constant, what you could do to make it, a different form, and how to manipulate equations so you can get the answer that you're looking for. And as you do these things, you should start to develop an intuitive grasp. You should be able to look at an equation and say, oh, I should be able to simplify it to something like this. And then once you start doing that, then you see an equation and you should be able to pull out, just by looking at that equation, you should see how these variables relate to each other. And you should start saying to yourself, well, if we hold all the other variables constant and I just vary these two, then I know that this is proportional to that, or this is proportional to that plus some factor, plus some term or something like that. And finally, recognizing equations and graphs. That just comes with experience. And that's really, I think, where a lot of the intuition comes from. And that's why lots of physicists think not of equations, but they think of graphs, and they do it. Actually, Isaac Newton's in the Principia Mathematica, he didn't use algebra. He used geometry to do a lot of the problem solving. He was doing calculus with geometry, which I think today even a lot of physicists still think in terms of graphs. They don't really think of equations. Equations are something you write down to really describe these graphs that you really want to draw. So algebra and physics, how do they go together? We do a lot of algebra. I just can't emphasize enough for you how important algebra is in everything we do. We've reserved a lot of variable names for physical constants, like c, h bar, and g, and things like that. There's a lot of these. Once you see them, you won't use them for variable names ever again. We also reserve a lot of variable names for specific rules. So in a problem, we have an object with a mass. We just say mass m. We just always use m for mass. So if you see m, you think, oh, that's the mass. V for velocity, A for acceleration, X for position, H for height, things like that. And there's like a whole encyclopedia of what we typically use variable names for. I think I saw once somebody built a table where they had a list of every letter of the alphabet and what they're typically used for. And oftentimes we use the same letter for different things. Or we use something, we have like different letters we might use for that. So we often talk about proportional and inversely proportional, as I described earlier. And it's important to know that physicists tend not to be too excited about the exact factor of proportionality. We just want to know that they're proportional. Okay. And we spend a lot of time looking at graphs, writing down the equations, or going vice versa. The key thing is, though, that physicists, we don't really care about specific problems. We're really looking for equations that show how real physical things in the universe relate to each other. The things that excite us is when we understand a rule about how any object that's moving interacts with any other object that's moving, no matter what their velocity or acceleration or mass is. That's where we really use equations. And we call them, I think we call them formulas is when we get to that point. So anyway, thanks for watching. I know this is a long video. I tried to make it short, but I kind of wanted to cover all the things that kind of go together in that ball of algebra together. So subscribe for new videos. Click like. It'll tell YouTube that this was a video that you want to see, and it will help other people find this video, and it'll help you find more videos that you might like. And if you have any questions, or if there's clarifications or errors, any kind of comment, just comment below. I'll try to get back to you soon. Thanks for watching, guys. Take care. Bye-bye.